In this section, we are going to discuss the field QP, the field of p-adic numbers. Recall that we have shown previously that this P is an integral domain. And as an immediate consequence, this P has a field of fractions. And that field of fractions is our QP. Just like Q, the field of rational numbers, is a field of fractions of Z, the ring of integers, which is clearly an integral domain. And we can state this as a definition. The field of p-adic numbers, denoted by Q sub p, is a field of fractions of the ring ZP. We can also formally view Q sub p as Z sub p adjoining an element. Indeed, by definition, any element in QP has a form of A divided by B, where A be in ZP with B being non-zero. And now recall by proposition 2 on page 12 of Sayre's book, we have that B is equal to some power of P times V for some invertible element in ZP. So we can write A over B as follows, where this part is clearly in ZP as a product of two elements in ZP. And this whole thing lives in the ring ZP adjoining P inverse. So we can think of QP as ZP adjoining P inverse. Now, every element in QP that is non-zero has a unique representation. This unique representation is PNU, where n is an integer, not necessarily non-negative, and U is in U, the subgroup of invertible elements in ZP. The existence of this representation is clear, because A over B, a generic element in QP star, is equal to some PM U divided by PNV. And this can be simplified to P to the power m minus n and UV inverse. And here m minus n plays a role of n here. For the uniqueness, we will simply invoke the corresponding uniqueness for the factorization in ZP star. Because suppose we have two factorizations, PMU and PNV, where m and n are both integers with m bigger or equal to n, and UV are both invertible in ZP. Then we discuss two cases. If n is non-negative, then m is also non-negative. Then this equation becomes the equation literally in ZP. But the uniqueness of the factorization in ZP, we are done. It follows that m must be equal to n and u must be equal to v. Now if n is less than 0, a negative integer, then we can multiply both sides of this equation by p to the power negative n. This negative n is positive. Now this follows that we have the equation p to the power n minus n u equals v. And this is again an equation in ZP. Now by the uniqueness of the factorization in ZP again, we must have m is equal to n and u is equal to v as well. So this verifies the unique factorization in QP star. Here again, this integer n will be called the p-adic valuation of the element x, and is again denoted by v sub px. And one has vp sub x being non-negative if and only if x is in ZP. And now, as an analog to proposition number 3 in the previous section, we have the following proposition 4, giving the topology on QP by the p-adic metric. The topology on Q sub p, the field of p-adic numbers, is defined by this metric. This is the definition for the topology on QP. Here we do not have a subspace topology. But under this metric topology, we have the QP is locally compact, and QP contains ZP as an open subring. And the field Q, the field of rational numbers, can be embedded into QP as a dense subset. But the same proof as in the ZP case. This D is again a metric. So now let us check the local compactness of QP. For any element x in QP, we claim that the collection of x plus p to the n times ZP for n equal to 1 form a neighborhood system of compact neighborhoods for x. So this can also be called neighborhood basis. Indeed, x plus p and zp is equal to the collection of elements in QP such that y minus x lives in Pn ZP. And this means the collection of elements such that y minus x is Pnu for some u in ZP. Here u may or may not be invertible. And this is the same as saying y in QP satisfies that Vp of y minus x, the p-adic valuation of y minus x, is at least n. And in terms of the distance, this means the distance is less than or equal to e to the negative n. And because this exponent here must always be an integer, dxy less than or equal to e to the negative n is same as dxy strictly less than e to the negative n minus 1. Because there's no value in between for d of xy under the p-adic metric. What does this tell us? This tells us this set is both closed and open. So x plus p and zp is closed and open in QP. And because x plus p and zp is contained in x plus zp, which is a compact space. Zp is compact. By the same proof, you can also see that x plus zp is compact. So x plus p and zp as a closed subset in the compact space is also compact. And self is open as well. So it's a neighborhood of x. And all of them form a neighborhood system of compact neighborhoods of x. And any neighborhood of x in QP, because those x plus p and zp are defined through metric balls, any neighborhood of x in QP must contain a neighborhood of this form. So they indeed form a neighborhood basis for x. And therefore this verifies this claim. And now let us see why Zp is open in QP. For any x in Zp, we know from the proof above, x plus p and zp is an open neighborhood of x in QP that is contained in Zp. X is in Zp and the p and Zp is also contained in Zp. So this sum is also in Zp. And it's an open neighborhood of x by the proof from here. So this verifies the openness of Zp in QP. And finally, let us see how the field of rational numbers is dense in QP through some embedding. We take any element in QP, which can be viewed as Zp adjoining P inverse. Now suppose Pmx is in Zp for some non-negative m. This m always exists because of this identification. If you multiply x by some power of p, the denominator can be eliminated. And we write Pmx as a compatible sequence in Zp. And now take yn be a rational number formed by the integer representation of the nth component of x divided by p to the power m. So this is viewed as a rational number. And we embed this yn into QP as yn with an arrow, p to the negative m, this infinite vector where all components are taken as x. This is in QP. And this part is in Zp. Now, by compatibility, we can rewrite this line as follows. For the first n components, they are x1 through xn. And starting from the n plus 1's position, all the terms are all equal to xn as before. So this is by the compatibility. Because this infinite vector lives in ZP. So the compatibility tells us xn is congruent to xk modulo pk. Or in other words, in the group A sub k, they are the same. This is for all k between 1 and n. Now, let us take the difference between x and yn arrow. X is equal to p to the negative m times this infinite vector. So comparing x with yn arrow, what do you get? You get when you take the difference, the first n components will vanish because they have the same first n components. So this is p to the negative m, and the first n components are zeros. And starting from the n plus 1's position, they might be different. And it follows that if you look at the distance between x and yn, by definition, this is e to the power negative vp x minus yn. And because the first n terms are equal to 0, we must have this guy less than or equal to e to the power negative n minus n. And now, at n goes to infinity, we have limit yn equal to x. And this verifies the density, and therefore the whole proof.